we look into the vertical structure of the atmosphere, specifically shown here is for the pressure variable. The figure on the left is the pressure and density variables of the atmosphere with altitude. The altitude is in kilometers, ranging from 0 to 500 kilometers. You can see here that the air pressure exponentially decreases as it goes from 0 to 100, 200, until 500. And this is also the same for air density, where the only difference between air density and air pressure is just a constant factor. And this makes sense because you see the relationship between pressure and density is proportional in the equation presented in the previous videos. Now, the air pressure and air density decreases exponentially because the amount of air molecules there are in the atmosphere. The air molecules tend to concentrate at the bottom of the atmosphere, and then it spreads out, or the concentration of air molecules become exponentially lower as we go up to the 500 kilometer level. Now, on the right is a zoomed in scale of the left hand figure from 0 to 30 kilometers, also in kilometers and in miles on the left and the right respectively. So here we see just the pressure. So at the surface of the Earth, the pressure is 1000 millibar, and millibar is another common pressure unit used for the atmosphere. 1000 millibar is equivalent to 1 bar, and 1 bar is the same as 1 ATM, or atmosphere, and that is equals to 101,325 Pascal. So from the surface of the Earth it is at its maximum at 1000 millibar, and it is exponentially decreased until 5.5 kilometers, which it goes to half of its original value of 1000, which is 500. And the distance between 0 to 5.5 kilometer makes up 50% of the atmosphere. Anything above that is the next 50%, which it goes from 5.5 kilometers up to 50 kilometers. So that also hints to the thinness of the atmosphere above 5.5 kilometers. At the top of Everest is at about 10 kilometers. That roughly equates to about 70% of the atmosphere from the top of that Everest until the surface of the Earth. And as it goes up, the pressure starts to decrease even more, so somewhere close to about 50 kilometers above the surface of the ground, the pressure is only 1 MB. Now, altitude, or the height above the surface, is usually reported in the pressure units, Pascal or hectopascal, or millibar and bar, or ATM. So there's a number of units that they use. We can calculate the pressure with height by using this equation. P is equals to P naught times exponent of minus Z over H, where P naught is the density of the air at the surface of the Earth, where Z is equals to 0, which is roughly about 1.25 kilograms per meter cube of air. And H is a constant, what we call the scale height, or the E-folding height, and this ranges from 7 to 8 kilometers. This is the height where it starts to decrease by 50%, as you saw in the previous slide. So it's about it's between 5.5 kilometers and 10 kilometers, which is roughly about 50% of the atmosphere. Is where below that 7 to 8 kilometers, it consists of about 50% of the atmosphere. And if you want to calculate the height, we just rearrange the equation to become Z equals to minus H multiplied with natural log of P over P naught, and we can calculate the height. The thing that changed here is the pressure, because and the pressure changes with height. So when we input the pressure at a certain height, and using the constants of H and P naught, then we will be able to calculate the altitude, or the height above the surface. This equation can be used to calculate the actual height. So by knowing the pressure, we can calculate the height because of the close relationship between pressure and height. Now we look at the temperature vertical structure of the atmosphere. Before that was the pressure vertical structure. We can separate the atmosphere into different layers based on the temperature profile of the temperature vertical structure. So that is separated by the changes in temperature, whether it's increasing or decreasing, because as you can see here, the atmosphere can be separated into four main layers: the troposphere, the stratosphere, the mesosphere, and the thermosphere. In the troposphere, we see generally the temperature decrease with height. And then when it starts to increase with height is where the stratosphere starts. And when it begins to decrease again is when the mesosphere starts. And so on until the thermosphere. So in the troposphere, somewhere below 20 kilometers, is where 80% of the air is located, as shown in the pressure vertical structure part. Now in the stratosphere, above the troposphere, this is where the ozone layer resides, and this is where it protects us from the UV light, harmful UV light of the sun. But in this layer is where, even though there are strong winds, but little mixing takes place, less turbulence occurs in this layer because of the absence of obstructions to restrict the flow or to obstruct the flow. In the troposphere, comparison, it has high turbulence. It might have strong winds, but it also have high turbulence because of the surface obstructions. In the mesosphere, the thermosphere contains, even though those are very large layers, it contains only 0.1% of the air, and because most, like I mentioned before, most of the air particles resides or exists in the lower layers or the 50% of the atmosphere, the bottom 50% of the atmosphere. So an example from the Wallace and Hobbs book on the use of that equation to calculate height from the pressure is this: assuming an exponential pressure and density dependence with the folding height equals to 7.5 kilometers. Remember that the folding height is about 7 to 8 kilometers. So here we choose the mean between those two values. We need to estimate the height in the atmosphere at which, question number 1, the air density is equal to 1 kilogram per meter cube. Now, recall that the average density of air is 1.25 kilograms per meter cube. So that means if it's at lower density, this height will be somewhere above in the atmosphere instead of at the surface. And question number 2 is the height at which the pressure is equal to 1 hectopascal. This is also a low pressure because at the surface of the Earth, the pressure is about 1010 hectopascal. So we start by using the equation Z equals to H natural log P naught over P, and just by substituting the value, H is 7.5 kilometers. Natural log P naught. P naught is the pressure at the surface, or the density at the surface. It's 1.25, and the density at that height that we want to calculate is 1. And by calculating this, then we get the height at which the density is 1 kilogram per meter cube. 7.5 times natural log. So this is at 1.7 kilometers from the surface of the Earth. Now you might ask, why am I using the density here instead of pressure? You must recall that pressure and density is directly proportional. The only difference is the gravity constant. So we can substitute density into this equation instead of pressure because of this relationship. Remember, pressure is equals to mass times gravity. So in the end, if you were to substitute this equation into this equation, then the constant would cancel out, and that's why we're able to use density instead of pressure. So in summary, when the air density has decreased into 1 kilogram per meter cube is when the height is at 1.7 kilometers. It's pretty high up into the atmosphere. This is for question A. And for question B, the height at which the pressure is equal to 1 hectopascal, we use the same equation. Height is equals to h natural log P naught over P, and we just substitute the value into this equation where h is 7.5, P naught, which is the pressure at the surface of the Earth, is about, let's use an approximate of 1000 hectopascal, and the pressure at that height is 1, and we calculate this, we'll get about 52 kilometers. So this is at the topmost of the atmosphere, where it's quite close to space, where it consists of maybe around 1% of the atmosphere. So where the amount of density or the amount of air molecules in the atmosphere is about 1%, the height is at 52 kilometers into the atmosphere, above the ground.